Hi, I'm Shan-Chang from Dartmouth College. I'm introducing our first speaker, Harry Arnold. He got his PhD in 2021, working with Jim Drake and Mark Swistig at the University of Maryland, working on non-thermal electron acceleration in macro-scale magnetic reconnection. Since then, he has been at the Johns Hopkins Applied Physics Laboratory, where he has been studying particle in cell simulations of thin current sheets with Misha Sinov. He's also a part of NASA Drive Center of Geospace Storms, where he has been building a gray box model combining data-based empirical reconstructions with the global magnetosphere model, MAGE, to more accurate model reconnection in the MagnetoTail.
Thank you for that excellent introduction. And also thank you to the GEM steering committee for inviting me to give this talk. Let me see, how well does the cursor show? Well, okay. So I'm Harry Arnold. I'm going to be talking about this new focus group titled The Kinetic Plasma Processes in the MagnetoTail During Substorm Dynamics, or KITS, is what we're calling it. This is just, a classic picture of the Dungy cycle. And actually, I'll show a video of that in just a moment. The outline of this talk, I'm sort of breaking it up into the different substorm phases. So we're going to start talking about the growth phase and the importance of thin current sheets there. Then we're going to move on to the onset of the substorm and the role of reconnection, maybe talk a little bit about where else reconnection might occur in the MagnetoTail. And then we'll talk a little bit about the expansion and the recovery phases and the role of bursty bulk flows and particle energization during these substorm dynamics. And finally, I'll talk a little bit about heavy ions and how they influence the substorm dynamics. So Dungy cycle, right? You can think of Earth as a dipole, but of course the solar wind distorts it. This is a great video from Wiltberger et al. 2015 that shows the solar wind hitting the day side. You get southward BZ that causes reconnection. That then stretches out the MagnetoTail and thins the current sheet usually before you get onset, and then you get bursty bulk flows coming towards the Earth, dipolarizing the atmosphere. But the key here is that the substorm begins with the equatorial current sheet thinning. So let's talk about the observations of such thin current sheets. So they're often observed with the LZ, it's the length scale normal to the current sheet near the ion Larmor radius, and as measured in the upstream magnetic field. So this is a distribution of current sheets, their width compared to the Larmor radius from cluster data. This is Runov et al. 2005. And a majority of them have that length scale being less than 10 times the Larmor radius, and a significant portion of them are even smaller than that. In addition, these current sheets can be very, very long, 20 RE. This is in the sort of XGSM direction. So down tail, they can be very long in length compared to their cross current sheet length scale. And finally, a characteristic of these thin current sheets is that you have the temperature decreases and the density increases. So this is just an observation of a current sheet. This red line here, this is BZ. You can see it thinning over time before onset occurs. And as it thins, the current density increases, the density increases, and the temperature decreases. So these are sort of characteristics of thin current sheets in the tail. Now, this was a recent work by Rogers et al. 24 showing the time spent in thin current sheets by MMS during these years. So they defined that by this kappa parameter, which is the square root of the ratio of the magnetic field curvature to the ion Larmor radius. When this is less than 1, the ions are demagnetized and you're in a thin current sheet. So this is each of these pixels corresponds to the time in seconds spent in the thin current sheet. And you can see that there are thin current sheets across the tail, although they are sort of dominantly on the dusk side. He also overplotted these little pink dots, which are MMS identified ion diffusion regions. These diffusion regions can correspond to X and O lines, which I'll talk a little bit more later, but they can indicate magnetic reconnection. So there's the thin current sheet is potentially important in this process. And it's everywhere in the tail, really across the whole thing in this YX plane. Yeah. So let's talk about the force balance of these thin current sheets. If you just consider it from an MHD perspective, right, you can balance the isotropic pressure in this Z direction across the current sheet with the magnetic pressure from the load and the pressure along the current sheet with the magnetic tension force. And if you do that, you arrive at this relationship right here. So this is the length scales of the current sheet along it and across it compared to the upstream magnetic field in the lobe and the magnetic field in the current sheet. But we know from observations that Bx over Bz is about 20. And if that's the case, then the length of our current sheet down the tail should be about 2 Re. This is an order of magnitude less than the observations, which say that it should be like 20 Re. Just for this 2 Re example, we're assuming that the cross length scale is about 1 Di, which is pretty consistent with these observations. So we can't get force balance of these thin current sheets with isotropic pressure. People have thought that maybe you can get it with anisotropy of the electrons. So when you take into account this anisotropic electron population, you can plot the J cross B force over the pressure gradient force. And if it's in force balance, then this should be unity. They should be the same and it should be balanced. But of course it's not. So this black line shows you basically what MHD would give you, which is not near unity. And even when you take into account electron anisotropy, you're still a little bit off. Further, from empirical models of the magnetic field, we get that the current in the MagnetoTail current sheet should be about 1 to 3 nanoamperes per square meter. But observations show currents significantly larger than that. This is taken from various distances along the tail, 18, 25, 40, 60, but almost all of these measurements are significantly larger than 1 to 3. And you can immediately see that if you have this off-diagonal pressure component, that's going to add an additional term to your current and can increase from what MHD would get you. So it looks like we need some sort of off-diagonal pressure. So let's take a look at the ions. So going back to this force balance equation, you have the isotropic pressure component, the electrons, and then the ion off-diagonal pressure compared to J cross B. You can see that if you have a gyrotropic and isotropic plasma, that off-diagonal pressure is just going to come straight out of P parallel and P perp, like this, according to this equation right here. So there's a thought that if you have ion anisotropy, maybe that will get you your force balance. And indeed, these are several different events. I think these are 20 observations here of current sheet thinning. So this is anisotropy versus BZ. So the thinning process is going to take you from the right side of these plots to the left side of these plots. And you see that for the ions, which are the blue dots, you almost always end up with a little bit of anisotropy at the end of the thinning phase. The electrons are in red for comparison. So work that I've done with Misha Sitnov has been based on those observations. We assume weakly anisotropic ions, and we come up with these equilibrium for PIC simulations. And a few features of this is firstly, you have an embedded thin current sheet. So this is the current right here, and it's embedded into a thicker plasma density sheet. You have isotropy right at the center of the current sheet, but it's anisotropic asymptotically. And you're agyrotropic, actually. So you don't have gyrotropic plasma here. They're unmagnetized right at the current sheet. And crucially, you have this off-diagonal pressure component that's giving you the force balance. So finally, on this page, I just want to point out that if you compare this thin current sheet equilibrium to a Harris current sheet equilibrium, where the thickness on the left side of this box is approximately equal, you immediately see that the thin current sheet is significantly longer than the Harris current sheet, which is what we're trying to do. So considering the force balance for a moment, this is the various terms in that sort of J cross B equal div P equation as a function of X going down the current sheet, right in the center of the current sheet. This black line here, this is your J cross B force, and the dashed black line is the sum of the divergence pressures. And since they're approximately equal, we see that we're in force balance. What's interesting is that the electron contribution, which are these blue lines, pretty small, negligible compared to the ions. And you have the ion isotropic pressure, which is this solid red line. But then the dashed red line, that's your off-diagonal pressure component, and that's actually quite significant here. So to understand why it's playing such a big role in the force balance, we look at these two cuts. This is now across the current sheet in the current sheet normal direction as a function of Bx here. And we plot the current and the density. And again, you see that the current sheet is embedded into this thicker density plasma sheet. But you also see that the thin current sheet reverses only about half of the asymptotic magnetic field. The rest is reversed by sort of a much larger scale much larger scale current sheet that the thin current sheet is embedded in. And when you come back to this equation here, which again, this does assume gyrotropic plasma, but this is your off-diagonal pressure component here. And you can rewrite Bx Bz over Lz as J cross B. The anisotropy gets you 0.1. And then when you plug in a half for this B squared, you find that the off-diagonal pressure is responsible for about 40% of the J cross B force in this current sheet. So the off-diagonal pressure is playing a big role in the force balance as expected. To understand sort of the plasma kinetics here, since this is an agyrotropic plasma, we consider these following plots here. So VR is the in-plane velocity, which is in GSM, you can think of it as Vx squared plus Vz squared. This shows the contribution to the total density as a function of VR. And this is the contribution to that off-diagonal pressure component. And you see that the ions producing the largest contribution to the pressure are superthermal ions, in fact. And when we run some test particles through our simulation, we get these orbits, which are your standard meandering Spicer orbits, as well as your figure-of-8 orbits. Yeah, so that's exactly what I said. But in these plots, we integrated over Vy entirely. So instead of doing that, if we integrate separately over these four regions of Vy, sort of your two tails, and then within a standard deviation of the mean, we can come up with these analogous plots. So this one is just like this. It shows the contribution to the density, and it's all pretty much as you expect. But the off-diagonal pressure component is dominated by this portion of the distribution. And it turns out that these ions are the figure-of-8 orbits, the figure-of-8 Spicer orbits. So in our approximate equilibrium, we assume Bz equals 0. If you look at the equations, that means that your off-diagonal pressure is 0, just analytically by symmetry. But when you have a non-zero Bz, like you do in the MagnetoTail, that's going to tilt your figure-of-8 orbits, and that gives you the off-diagonal pressure. So the point here is you need this off-diagonal pressure to get the thin current sheet force balance that is observed in the MagnetoTail, and that's provided by these figure-of-8 Spicers. So I want to switch gears a little here and talk about some data mining reconstructions. I think this is a really powerful tool that shows a data-based sort of global picture of what's going on in the MagnetoTail, and it can really illuminate some of the issues. Just to explain how it works, this is work done by Misha Sitnov and Grant Stevens. They have a database of about 10 million magnetometer measurements that they characterize in this 5-dimensional state space. You basically have your substorm index and time derivative that gives you the phase of your substorm. Similarly, for your storm, gives you the phase of the storm, and you also have this solar wind driving electric field. When they do this, they can take, say, the 30,000 closest magnetometer measurements to a particular point in time, and they can fit a magnetic field model to those points. So this is an example. Each of these gray dots is one of those closest, nearest neighbors magnetometer measurements, and then you can get a magnetic field that even resolves X lines. Which is quite impressive. But an interesting part of this is that in their magnetic field model, they have a thick equatorial current sheet and a thin equatorial current sheet. And what they've noticed is illustrated in this plot here. So this is several different parameters, but I want to point out a couple things. This plot shows the thickness of the thick current sheet, which is a few RE, and it also shows the thickness of the thin current sheet, which is a fraction of an RE. It's like a DI, which agrees exactly with observations. And for each of the substorms that they've modeled, they get pretty much the same thing. In the growth phase, the thin current sheet builds up. This is illustrated by this figure here, where they've totaled the current in the thin current sheet. And you can see it increases in the growth phase. And in the decay phase, it goes away. And this agrees with observations, as well as thin current sheets are typically observed in the thin current sheet. This reconstruction model is also capable of seeing BZ humps that can lead to near-Earth dipolarization. I'll talk a little bit about that later. This is just another example of their reconstruction. We have this top row is the growth phase, the bottom row is the expansion phase. You have BZ on the left, the current in the middle, and then the meridional plane on the right. So the 4 plots on the left, those are all equatorial plane plots. So you have a BZ hump, but you also have this thin current sheet in the growth phase. And this thin current sheet spans almost the entire width of the MagnetoTail. It's huge. Although I should be clear here, it is huge in the X and Y plane. It is very thin in the Z dimension. So that's what makes it the thin current sheet. And after the expansion phase, you do get an X line in the reconstruction, but the thin current sheet pretty much vanishes. So it's no longer there after onset. So now let's talk about onset and the role of reconnection. First, a quick refresher on reconnection, just so we're all on the same page. You start off with oppositely directed field lines above and below a current sheet. These then reconnect at this X line where the plasma is demagnetized. The newly reconnected field lines then shoot out on either side at roughly the upstream Alfvén speed. In MHD simulations and in PIG simulations, you often get these things that are called plasmoids or magnetic islands or flux ropes. And these correspond to O lines, just like this, where the reconnection occurs is the X line. And you also get heating. So this is just showing the change in electron heating as a function of the upstream Alfvén speed. And you can see that they agree quite well with each other, basically saying that the more upstream magnetic field you have, the more heating you're going to get in reconnection. And this is from a simulation, a macro scale simulation now, looking at the electron distribution. And you can get really hard power laws illustrating that you can produce a lot of non-thermal electrons as well, and ions also, from magnetic reconnection. So you get both heating and non-thermal particles. So going back to onset now, historically, there have been sort of 2 ideas how you might get it. The inside out, which basically says that you have some current sheet disruption closer to Earth that launches a rarefaction wave out and gets you reconnection further out. Or outside in, where you have reconnection further out, that creates flows coming inward and disrupts the current sheet closer in. This is a really nice observation from a famous Angelopoulos 08 paper, where there was a fortunate alignment of the Themis satellites, and they inferred that there was reconnection sort of right at this X line. And in fact, when they timed everything out, they get reconnection occurs, then you observe it at P1 and P2, then you get auroral intensification in the substorm onset, as seen in the ionosphere, and then you get dipolarization in the inner magnetosphere. The inside-out onset idea is a little different. These are pictures of the aurora, the auroral arc, and this is right around onset here, and then you get this nice beating structure. And as time goes on, the auroral arc moves poleward and eventually turns into this north-south streamer, illustrating reconnection happening after the onset. And interestingly, this is from a Sarathia 2020 paper. This is possibly one of the highest resolution global magnetosphere simulations done. And what they saw, you can actually see the grid scale in this zoomed in picture right here, but they saw this ballooning interchange instability in the near Earth magnetosphere that is theorized to cause these beating structures in the aurora. So there might be something in this inside out versus outside in, and perhaps a combination of the 2. I hope to explore this more in our joint session with reconnection later this week. Going back to the data mining reconstructions for a second, though, with the question of onset, this is a substorm that they reconstructed several slices for. These 3 plots here, these are the growth phase. So what you're looking at is the BZ field in the equatorial plane with various contours, different values of BZ. But what's interesting is that you have this big BZ hump at around 40 RE in the tail that stays there for about 40 minutes. Now, BZ humps should be unstable kinetically to the ion tearing instability, and they should be unstable in MHD to ballooning interchange. So it's a little strange why it's there for 40 minutes. But after onset, the BZ hump is drastically reduced, and you get this dipolarization in the inner magnetosphere with an X line in its wake. So this is a little strange, but what's particularly interesting in this is that if you look at the current sheet now, you see that there's this large, thin current sheet right in front of the BZ hump. And so there's a question of, is the thin current sheet more stable to BZ hump instabilities? What's the interplay there? And this is very much an ongoing question. But on the note of thin current sheet stability, I do just want to point out briefly that these thin current sheets are often observed with a polarization electric field, which is an electric field pointing towards the current sheet. These three plots here, these are three different PIC simulations where they have a polarized hot current sheet, a polarized cold current sheet, and an unpolarized current sheet. You can see these top row, this is the plasma density, this is the current density, and then this is the electric field. And you can see for the polarized cases, you have a thin current sheet embedded in a thicker plasma sheet. They then drove these simulations with some solar wind-like electric field. And of course, they eventually got reconnection in these simulations. But what's interesting is that the polarized current sheets actually reconnect much later than the unpolarized current sheet, suggesting that these thin current sheets might be more stable to reconnection type instabilities. And they theorize that this is because of that thicker plasma sheet preventing it from reconnecting. So moving on, I want to talk a little bit about after onset when you get BBS and particle energization. This is from the model APEC, which has a MHD backbone, and then inside of it is a PIC domain where you can resolve kinetic physics. And these are two-way coupled to each other. And what they've done is I think, very interesting here. They've followed a bursty bulk flow through time, and they've taken various electron velocity distribution functions along that bursty bulk flow. So I don't know how well this is visible, but A, B, C, D, E, F, these are the locations of the different distribution functions. The top row and the middle row are taken at the exact same location, just different times. And the bottom row is taken at a different location, but sort of analogous. So such that A is in front of the bursty bulk flow, B is right at the peak, and then you go tailward after that. What's interesting is that, especially for the low energy right at the peak, you have parallel heating, which they attribute to Fermi acceleration, which you can get basically from conservation of the second adiabatic invariant. The perpendicular heating is betatron, which you get from the conservation of the first adiabatic invariant. And the combination of these two, like this, is often called a rolling pin distribution. So it's very interesting that right at the peak here of the dipolarization front of bursty bulk flow, they have this rolling pin type distribution. You can contrast this with some observations. Now, this is cluster data, so some time ago. And they're mostly just looking at this super thermal part of the electron distribution, say 50 to a couple hundred keV. But here, right in front of the dipolarization front is where they get their rolling pin distribution. And after they are in the actual dipolarization front, that perpendicular population is lost, they suggest, due to scattering. Interestingly, for this third event here, they have that rolling pin distribution for some time after they enter the dipolarization front before it scatters away. But here they're actually showing that the higher energy population in the bursty bulk flow is more parallel rather than perpendicular. So I think that there's a lot of interesting results here. I mean, I think most people would agree that Fermi and betatron are playing big roles in the heating process, but I think the details are not fully understood or potentially a little contradictory between events and simulations, even between simulations and events and events. Yes, and there's the cigar distribution. I also just want to point out that previously, these observations are showing a couple hundred keV, which tends to be the maximum energy that people talk about for electrons in the MagnetoTail. But this is actually recent observations from Elfvane showing precipitation from the plasma sheet. Let's see if I don't, oh, that's a shame. At the top here, if this zoom bar goes away, you can see the different regions of the magnetotail labeled. But the point is that this is your plasma sheet, and this is showing precipitation from the plasma sheet more than a few MeV electrons coming from there. So there's a bit of a puzzle as to what this maximum energy is. Well, sure. Thank you. Yeah, so you can see the plasma sheet is separated from the outer radiation belt in the plasma sphere. Okay. And finally, I want to sort of make this point about how all these things can sort of tie together, right? So in the growth phase, you have this thin current sheet, eventually onset occurs, you do get reconnection, and that can lead to bursty bulk flows, intermagnetosphere injections, and the buildup of the ring current. Now, the ring current is biased towards the dusk side, and it has often been suggested that that can actually inflate the magnetic field behind it, which you can just get from sort of the right-hand rule. You can see that that must inflate the magnetic field behind the ring current. If that happens, then you can imagine that reconnection happens on the dawn side, resulting in bursty bulk flows on the dawn side that can then disrupt the dawn side current sheet. And so that's what these images are showing here. So these three plots, these are at different times in the YZ-SM plane showing the current sheet. So you get some thinning, and then you get this dawn side disruption rather than a symmetric disruption. And on the left, you can sort of see why. This is the residual magnetic field, which basically means the BZ without the dipole component. And you can see that it's being dipolarized on this day side, largely from bursty bulk flows coming from down tail. And so this whole feedback process, I think, really illustrates the importance of all of these kinetic features in the magnetotail and how they interact with one another. Finally, I want to talk about heavy ions, because basically up until this point, I've pretended that the magnetotail just has protons and electrons, and that's not really quite true. So in the magnetotail, you can get oxygen coming from the day side and sort of going straight back to where reconnection occurs, and from the night side, just entering the plasma sheet directly. Interestingly, the dependence of oxygen is a function of both solar radiation and geomagnetic activity. Basically, as there's more output from the sun, you get more oxygen in the magnetotail, and as there's more storm-like activity in the magnetotail, you get more oxygen. And you can see why it's often somewhat ignored in various simulations, because the ratio of oxygen to hydrogen is usually quite small. And so you can say, well, maybe we can just neglect it. It's not a big part of the population. Plus, if we're including oxygen in all this, that just makes things very difficult computationally. But as you go to larger and more powerful storms, oxygen definitely plays a larger role. And this really illustrates the difficulties in capturing oxygen in simulations, because it introduces a third scale, a third length scale, right? So this is just sort of a standard reconnection picture. At the very center, you have the electron diffusion region where everything is unmagnetized. Going out, you have the ion diffusion region where the electrons are magnetized. And then now you have the oxygen diffusion region where electrons and protons are magnetized, but oxygen is not. And only outside of that do you have a full magnetized plasma. And you can see that quite clearly in these simulations on the right here, where it's showing the ageirotropy of the different species. So the electrons, very small, right in the center. Protons are a bit bigger, and then oxygen is just huge compared to everything else. So when you include oxygen, you're including this third length scale, and that makes everything a little bit more complicated. Interestingly, and when you look at, say, the reconnection rate, you should expect the reconnection rate for more oxygen to lower. So the more oxygen you have, the lower your reconnection rate. And that's showed in these simulation results right here. This is the reconnection rate as a function of time for different simulations. So the blue and the green line have very little oxygen. They have the largest reconnection rate. Red has oxygen, but just in the lobes, not in the current sheet. And so that's already reduced. But then when you add oxygen in both the lobes and the current sheet, that reduces the reconnection rate even further. And so that makes sense because you're increasing the mass density, and so that should decrease the reconnection rate. What's strange is that the opposite appears to be true in the MagnetoTail. Basically, the more oxygen you have, you delay the onset even further. Basically, the more pressure you need to have built up in the lobes to get onset. And then once you have onset, the unloading rate increases with the more oxygen you have. And the argument goes something like this. Basically, because you need more magnetic pressure in the lobes to get to onset, that increases the numerator of your reconnection rate much more than you're increasing the denominator by increasing the mass density in the tail. And so the more oxygen you have in the tail, the faster your reconnection rate, and that's just illustrated here. So this is reconnection rate as a function of the oxygen to hydrogen ratio. So to conclude, there are a lot of open questions here. I definitely didn't cover everything. I was trying to keep this sort of broad. There were a lot of material that I didn't get to include. So if you feel like I missed something, I definitely did, and I apologize for that. But here are some questions that come to mind for me. And first and foremost is what governs the thin current sheet stability, because it seems to be playing a big role in determining the nature of onset. And it's not totally clear what makes this more or less stable than Harris current sheet and what the details there are. In particular, there's this question of the polarization electric field in the thin current sheet. Of course, where does substorm onset occur? I think that this is still an open question, although obviously reconnection is playing a very important role there. And what are the details of the particle energy gain in the tail? How will that feed back on the system as a whole? Obviously, Fermi and Betatron are both very important, but I think that there are some open questions there as well. And then this introduction of oxygen, I think, is very interesting because that third scale that you're introducing must modify the thin current sheet and its stability quite significantly. And I really don't know how that plays out at all. So I want to take a minute and just advertise a few things that I think are of broad interest to the GEM community. The first of which is Mike Wiltberger is giving a tutorial on Friday afternoon. So if you're here, I do encourage you to go and see that. He's the MAGE model has just been released at CCMC, and he's going to be demonstrating how to make runs and analyze the runs. So I encourage people to go look at that if they're interested. Okay. The next thing I wanted to advertise is in October, late October, there's going to be a workshop at APL in Maryland looking at this Gannon storm or Mother's Day storm that just occurred. It was one of the strongest storms basically in the space age. And there's this goal to, unite everybody and really come and talk about it, maybe even get some publications out of it, a special issue or something like that. So if you have questions about this, if you're interested about this, I encourage you to contact Noor for more details. And finally, there's going to be a CGS workshop in November, but right before that, there's a graduate student workshop as part of the CGS effort. This again will be at APL in Maryland. And I think it'll be a great opportunity for graduate students, tutorials, hands-on training, more about the MAGE model. And there's even a limited number of travel grants to support attendance. So definitely encourage you to look at this if you're a graduate student. And then this is my last slide, just the KIT sessions that are this week. First, later today, there's one on thin current sheets, their formation, their location, their stability. I'm very excited about this one. I think we'll have some good talks and good conversation. Note, this time is wrong. That's my fault. I don't know where I got these numbers from. It's not right. It's going to be 10:30 a.m. to noon. So it'll be after this session. Then on Tuesday afternoon, that'll be the KITS poster session. I know Akhtar and myself will both be there looking at all the posters, trying to get some good conversation. Unfortunately, our two co-chairs, Jason Durr and Anton Artemiev, couldn't make it to GEM this year, so they'll be with us in spirit. On Wednesday, we'll have a joint session with Reconnection, looking at the importance of reconnection throughout the MagnetoTail. And then Wednesday afternoon, we'll have one about plasma populations, looking at oxygen and heavy ions in the MagnetoTail. And finally, on Thursday, we have a joint a joint session with the MESO focus group, looking at different energization mechanisms for the different species in the MagnetoTail and how that affects the near-Earth transition region. All right, thank you again to everyone for listening to my talk.
We have a student sorry, we have a student moderator who will be helping taking the questions in.
You have any hands?
Thank you for the very nice talk. I'm new to this MagnetoTail physics, so I think I missed the some of the key point of oxygen plus O plus, how that will impact the globally and locally. Do you mind revisiting that one just briefly again? Thank you.
Sure. Yes. So I think the key with oxygen is I think it's at least micro scale thinking is really this slide, because it introduces this third length scale. So I'm a simulation guy. That's how I like to think of things. And simulations are already quite expensive, and introducing this third length scale is going to make things even trickier. But at least for this slide, you can see the azeotropy parameter for electrons, protons, and oxygen clearly show the three length scales in this reconnection simulation. But on a macro level, I guess just briefly, I'll say you would expect from this micro scale thinking that the influence of oxygen would lower the reconnection rate, but apparently it increases the reconnection rate. And I think the sort of broad aspects of this are fairly convincing, that it's because you have this increased magnetic pressure in the lobes before you get to onset. But I think there are still questions about the details of that process and how that works, and especially the relationship between the oxygen effect and the thin current sheet stability that I spoke about earlier.
Dolores, you have a really nice example of a dawn-dusk asymmetry that develops because of the diversity bulk flows and the injections. Does that slosh back and forth, or is that something that goes first with the energy going into the dusk side and then swinging around, or does it eventually even out?
That's a really good question. I will say, this is not my paper, so I'm not 100% here. I would expect some sloshing back and forth. I mean, certainly there's the initial one, right, where you build up the ring current, and then the ring current inflates the MagnetoTail on the dusk, and then that causes the reconnection to continue only on the dawn. But I'm not sure how much that affects. If I recall in the paper, I think they did say that this effect here, where you get this dawn site disruption, does sort of restore some current symmetry in the ring current, but I'm not 100%.
Just have next. Yeah. Okay, as one of the older guys here in the audience, I mean, I was at the very first year meeting. The conclusion slide you showed was really interesting, because that could have been from 30 years ago. I mean, it was the same questions, I mean, about thin current sheets and all that. But now, more specifically, I mean, you showed that reconstruction of the thin current sheet, actually, I mean, before onset during the growth phase. Well, we know from observation that when this whole thing breaks up, it doesn't break up, I mean, all across the tail. What we see are those diversity bulk flows, that they're very localized in azimuth, or in y direction. So the typical scale length is a few RE, I mean, 2 to 4 or so, 2 to 6 RE. So, is there any explanation for that? Would that possibly have to do something? I mean, with the oxygen content? Did anybody look at that?
So that's a great question. To your first point, just going back to the conclusion slide, I think that these questions are longstanding, but we have slowly been coloring them in But I think that there are still, you know, they're not fully answered. Going to sort of your main question here about the dawn dusk length scale of these bursty bulk flows, I'm not sure that that is fully understood. I wouldn't expect oxygen to be playing a big role in that. Let me rephrase. Because you have that same dawn dusk width in substorms and storm time substorms, where you would have a lot of oxygen in the tail and not a lot of oxygen in the tail, I wouldn't think oxygen to play like the dominant role in determining that length scale. But I don't know the answer of why it's 1 to 3 RE.
Thanks.
But a great question.
Hi, great talk, Shannon Hill in the back here. Hi. So you talk about thin current sheets and they can be embedded in like a thicker current sheet. And then you also talk about the ion anisotropic pressure being important for the thin current sheet. So I'm curious if we're seeing a thicker current sheet also further down tail, and if the ion anisotropic pressure is also important for the thicker current sheet being further down tail.
So I believe that there is a thicker current sheet. The thin current sheet isn't embedded in a thicker current sheet, but I think the thicker current sheet can be well described by your sort of standard isotropic Harris equilibrium. And it's really the thin current sheet that is breaking that model. So I would expect the off-diagonal pressure to really only be important in the thin current sheet. And part of the reason there is also because it looks like these figure-of-8 Spicer ions are what's giving you that off-diagonal pressure, and the length scale of sort of their effect is set by the Larmor radius, because that's what's determining their figure-of-8 orbits. So I wouldn't expect much of a off-diagonal pressure component outside of that figure-of-8 range.
And the location further down tail versus up tail.
I mean, yeah, you can certainly get thin current sheets way down tail. I would expect there to be, they are also embedded in a thicker current sheet, but I guess I don't know. I mostly think about in the sort of 20 to 30 RE range of thin current sheets. So I'm not quite sure.
Okay, great. We can talk more about it. Thank you.
Hi, very nice talk. I have 2 questions. The first question is on the agiotropy calculation. How do you calculate the agiotropy from your simulation or from the observation?
Yeah, so that's a great question. I know let's see here. I talked about agiotropy twice. So in the PIC simulations, the thin current sheets that I did, I was using the Swissdac Q parameter. Mark Swissdac had a paper in 2016 where he talks about agyrotropy and how you can get it from the pressure tensor. For the ions, I think there was an equation up right here. And this is how they define their agyrotropy parameter, which I think is different than the Swissdac parameter.
I see. Yeah, and the second question, for the MagnetoTail plasma is typically in the conditionless regime.
Mm-hmm.
And under conditionless regime, the plasma distribution is not really in good max reading. So in that case, how do you define the pressure? It's a really naive question.
No, that's a great question. Yes, in that case, because it's not, I mean, basically you have a pressure tensor, right? That's the strict definition. You get that from the integral of F times, V vector, basically. And that gets you a 3x3 pressure tensor. And it's only when it's isotropic that reduces to a diagonal tensor where each of the components is equal to each other and you have isotropic pressure. But you're right, in the MagnetoTail, you don't really have that. And so you have a full pressure tensor, and that off-diagonal pressure component that I was talking about, that's coming from one of those off-diagonal components.
Thank you.
Mm-hmm.
One more in the back, maybe, and then we should move on after that. So we have enough time. Do you want to run back there? Thank you.
Thanks. I thought that was an excellent talk. Nevertheless, I still don't know much about this field. So naive, broad brush question. I mean, overall, you have led me to think that MHD really just doesn't have, just isn't adequate to describe most of the stuff you've been talking about. But my impression is that the people who do MHD feel like they do get the gross features of things pretty much right. And at one point in the middle of your talk, you were saying something about high resolution image simulations, actually, doing at least something well. So how do I think about reconciling those? Or is that question, one of the main points of the whole focus group?
I mean, that's honest. That's a great question. I mean, first, it should be stated, MHD gets a lot right. And even if it gets it wrong, it's sort of qualitatively right. Maybe their reconnection isn't happening in exactly the right spot, but they're getting reconnection in the tail. They get bursty bulk flows from that. They get inner magnetosphere injections. I mean, they're really getting the broad strokes at 100% right. I think the question comes down to sort of the details. And as far as the thin current sheets go, it can't be done with MHD. You need something more. And definitely one of my research projects right now is trying to figure out how to put more kinetic features into MHD models. I'm approaching it from this empirical reconstruction perspective, but of course there are efforts for multi-fluid, Hull, and things like that. Hybrid codes, the APEC, which is PIC with MHD. There's a lot of efforts to put these non-MHD physics there, but it is true, and this should be said, MHD simulations get a lot correct. So I don't want to, I don't know what the word is, insult MHD people.
There's a question online here. This question online. Why in the data mining was AL chosen a subset to AE?
Why was AL chosen as opposed to AE? Is that the question?
Yes, yes.
I don't know the answer to that. I think AL is just often chosen as a substorm index. I'm not sure if there was a specific reason why it was chosen over AE beyond that. The key there is just you want to capture substorm dynamics and storm dynamics, so you need something, but I don't know why AL over one of the other ones.
Okay, I think we're gonna thank our speaker.
Thank
one
you
more
so
time.
much.